So let's say you had a string here and you give that string a little yoink up and down. You'd see a little wave pulse travel down that string. But here's a question. If someone else on the other end of this string also sent a wave pulse down the line toward the first wave, what would happen when they overlap? So let's try to figure this out. Let's say you had a wave coming in this way, and yes, this is square. Kind of weird. It'd be hard. You have to be pretty talented to do this on a string. But this doesn't have to be a string. Let's say it could be a sound wave, an electromagnetic wave, any wave at all. The fact that it's a square is just going to make it easier for us to analyze. So you got this wave coming in this way, and then another wave coming in this way. So to be clear, this is the same string. There aren't like two strings here. There is one string, two waves coming at each other. So to be real, I mean, honestly, there's only one string. So this should be string coming here, and then there's a pulse up this way. So this string shouldn't be here. This string moved up to that point. It got disturbed. Then it comes back down to 0. And then there shouldn't be two strings here. You don't have two strings in the same spot. So this would be the string up there, and then it comes back down. But in these examples, I don't want to have to erase these all the time. It'd make the video really long. So let's just, anytime there's a string underneath a pulse, we're just going to pretend like there's no string in there. So what would happen? What would happen when these pulses overlap? Well, let's just find out. If I take one and I move this here, and then another wave is going to move over the top of that one, I'm going to get wave interference. This is the term, wave interference, for when two or more waves overlap in the same region. So what's going to happen? Well, the string can't be in two places at once. There can only be one string and one shape of that string. And the way you find out what the total wave is going to look like is simply by adding up the contributions of the two waves that are overlapping. So in other words, if I want to know the height of the total wave, I'm going to call that height YT, T for total. That's just going to equal the height of the first wave, I'll call that Y1, plus the height of the second wave, and I'll call that Y2. So if you're familiar with the wave equations, you could just plug in those two wave equations here, add them up, and you get a total wave equation. But a lot of times you don't have to resort to the full-blown mathematics of the wave equation. You can kind of just look at the picture and figure out what the total wave would look like. So let's do that. Let's put a little backdrop here so we can add these up. So we'll call this 1 unit high, and this is going to be 2 units high, and this is going to be 3 units high. It could be meters or centimeters, but it doesn't matter. We'll just say 1 unit, 2 unit, 3 unit. And now to figure out what the total wave is going to look like, I just add up the contributions from each individual wave. So both waves are 0 over here, so that's easy. 0 plus 0 is 0. And then it gets to here. The blue wave, we'll call that wave 1, has a value of 1 unit high. The pink wave, we'll call that wave 2, has a value of 2 units high. They're going in different directions, doesn't matter. Right now they're overlapping. So 1 unit high plus 2 units high is going to be equal to 3 units high. My total wave would look something like this. So if I were to ask what would the wave actually look like, the string, if this were a string, would actually look like this. It would just be one big 3 unit high wave while those two waves are overlapping. So that one was kind of easy. How does this get harder? Well, let's say we ask the question, what do these two waves look like when they're only partially overlapping? So maybe when they get to this point where they're only halfway overlapped, what's that total wave going to look like? We're still going to use this rule. We're going to add up both contributions to get the total. So over here, we have 0 and 0 plus 0 is 0 until you get to here. Now the blue wave, wave 1, has a value of 1 unit high. The height of this wave is 1 unit. The height of the pink wave, wave 2, is 0 units. 1 plus 0 is 1, so my total wave would look like this in that region. And now in this region, the blue wave is 1 unit high, the pink wave is 2 units high, 1 plus 2 is 3, so it would look like this in this region. Now over here, since the blue wave dropped down, we have to figure out a new value. So the blue wave has a value of 0, the pink wave has a value of 2, 2 plus 0 is 2, and so my total wave is going to look like this. So the total string, when those are overlapping halfway, would look something like this, which if it was a string would be really hard to do because it's hard to get an exactly square wave, but electronic signals can have square waves, and this is what they would look like if they were overlapping. Now I want to warn you about one thing. This idea of wave interference is a cool idea, but you got to be careful. The term interference is a little misleading. Yes, while these waves are overlapping, they create a different wave. They get distorted because the total wave will be the sum of the two waves, but these waves pass right through each other, which is great because when our phones send out a text message or a call to someone else, everyone else's phone is also sending out a message in that same air. Those electromagnetic waves are traveling right through each other. If they bounced off of each other, right? If these waves like bounced or got corrupted and the information got changed so that the shape isn't the same after as it was before, it'd be really hard to make phone calls and send text messages. But the wave interference is only happening while they're overlapping. The waves make it through unaffected. So the interference is only happening while they're overlapping. Otherwise, they pass right through each other unaffected, which is good. So let's look at one more example that's a little more challenging. So I'm going to get rid of these. And let's say you had these two wave pulses, the same square pulse, but then you got this weird triangular pulse coming in, and they're going to overlap. So this wave pulse makes it to here. This triangular pulse makes it to here. Oh, and you get the state of Nevada. So the string is not going to take the shape of Nevada. The string can't be in two places at once. So what's our total wave going to look like? We're going to use the same rules that we did before for wave interference. We're going to add up the values of each wave at a particular point to get the value of the total wave at that point. So what do we get? We've got 0 plus 0 over here, so that's easy. And now at this moment, the value of the blue wave is 1. The value of the pink wave is 0, so 0 plus 1 is 1. And in here it's a little weird, like you've got this pink wave changing, but over here it's easy, because the blue wave has a value of 1. The pink wave, let's assume this drops down 1 as well, so this is a -1 unit. Blue wave is 1, pink wave is -1, that's going to be 0. 1 plus -1 is 0. And after there, it's going to be 0. But what is it in between? Well, the simplest answer is actually the correct answer here. It just drops down like this. Why does it do that? Well, let's consider a point in the middle. This point in the middle, this blue wave has a value of 1. The pink wave has a value of -0.5. So 1 plus -0.5 is positive 1/2. Or consider a point over here, the value of the wave right here. For the blue wave is 1. The value of the pink wave is like -3/4. So the value of the total wave would be positive 1/4. That's why this drops down linearly. If this is linear, this pink wave just keeps taking a bigger and bigger bite out of this blue wave. And the total wave would look like this. So if we get rid of these, this would be what the total wave looks like when these two waves overlap. So I should say that this technique of just adding up the values of each wave at that point is called the superposition principle. It's a very lofty, intimidating name for something that's actually pretty simple. To find the total wave, you just add up the values of the individual waves. So recapping, wave interference is the term we use to refer to the situation where two or more waves are overlapping in the same region. And to find the value of the total wave while they're overlapping, you can use the superposition principle, which just says to add up the values of the individual waves at a given point to find the value of the total wave at that point.